Hello, everyone. We will begin the Genz webinar, Emerging High-Speed Interconnects and Genz Fabric, in just a moment. We're going to allow a few more minutes for folks to join, so please sit tight and we'll get started soon. Hi, if you're just joining, we will be starting our presentation in just a moment. We're allowing a few more minutes for folks to join, and we will get started in about 45 seconds. Hello, everyone, and welcome to today's presentation from Genz. This is our third webinar, and the title of today's webinar is Emerging High-Speed Interconnects and Genz Fabric. Presenting today will be Greg Casey, an engineer with Dell EMC, and John Norton, distinguished technologist with HPE. Greg has been involved with server architecture for both rack and bladed servers, and his focus over the years has been high-speed interconnects and the relationship with server architecture. Besides his heavy involvement with Genz, Greg is also on the board of the PCIe SIG. Welcome, Greg.
Morning.
John is a mechanical engineer and has developed numerous rack and blade server products while actively contributing to a range of industry standards and open development efforts. John has led the mechanical standardization group within JEDEC for 8 years and was recently named to the JEDEC Board of Directors. Hi, John.
Hi, happy to be here.
So today, John and Greg will be discussing the real-world problems involved in modern server design. So Greg, John, could you both tell us about some of the problems or challenges that your customers have indicated?
Yes, Rachel, we'll move on to the next slide. Our customers are demanding a growth in functionality. They're requiring significantly more memory addressable by servers to solve their problems. Currently, servers are configured with far more than 1 terabyte of memory. Customers are asking even more memory. Over the years, we've engineered methods of increasing our memory by utilizing multiple CPUs and using their memory to contribute to the overall problem-solving memory. But using standard networking and RDMA approaches, the user can get access to large pieces of memory, but it's at a cost of additional CPU resources, chassis resources, and additional latency throughout these layers. Over the past several years, the industry has witnessed the growth of domain-specific processors. You might ask, what is a domain-specific processor? Essentially, it's a general non-general purpose computer or device or piece of silicon that is enlisted to accomplish some specific purpose-based compute task. 2 examples of this are GPUs that have been enlisted to do compute tasks and the emergence of FPGAs. Persistent memory is maturing to the point where it can be utilized directly by the enterprise-level server designs as main memory. A term that we have coined in the industry is storage class memory, which is defined as a high-performance, highly reliable, persistent memory. The memory itself is changing as well. The ability of a memory subsystem to accomplish computation or data reduction as an architect has architectural advantages to the overall system designer. The movement of data does not really contribute to the actual solution of the problem and is really a waste of time and resources and expense. Security continues to be a paramount requirement for all of our customers. Keeping data safe, of course, is important, but the whole concept of root of trust is fundamental to all modern servers. All hardware, firmware, and software components must have verified heritage to ensure their authenticity and prevent rogue elements from infiltrating our system.
Thanks, Greg. Yeah, that's right. So customers want all of these new functions and technologies as soon as they're developed, and that's often sooner than is possible due to the existing architectural constraints. That's because in existing architectures, the CPU is at the center of everything. And despite the fact that these new technologies are developing outside of the CPU ecosystem, customers are unable to take advantage of them until the CPU is upgraded to support it. This usually comes in form of total replacement of the systems or a whole rack of systems. So in addition, these customers continue to face cost pressures and are always looking for ways to lower both capital and operational costs. And so that complete replacement or tear up, it contributes directly to the high cost of adoption of new technology. On top of that, the compute resources currently available to them are underutilized due to the nature of the current server design being tied to the CPU. So as an example of that, if a customer wants to scale their memory today, they must scale CPUs simultaneously. And inevitably, this leads to an imbalance in the system and inefficient use of those resources. In addition, customers that invest in existing scale-out memory deployments, they do so over proprietary protocols, and this results in vendor lock-in at a time when the industry in general is pushing the opposite direction to more open environments.
I agree, John. There are several electrical issues that I've noticed that are causing significant challenges for server designers. Large pin count devices. Modern CPUs have pin counts that exceed 400 pins or balls, which implies significant PCB layers for effective signal escape from those ball patterns. Additionally, the number of memory channels and associated physical DIMMs increase. PCIe lane count is also increasing. The utilization of these lanes are not only for historic PCIe add-in type cards, but the addition of large number of NVMe disk drives. PCI has always had issues of topology, which constrains server designs. As I mentioned earlier, memory channel counts are on the increase, and this problem is complicated that DDR speeds are also increasing. The ability to run these memory channels at the highest frequencies possible with multiple DIMMs in the same channel is becoming more and more difficult. The DPC, which we call DIMMs per channel, is approaching 1, going down to 1 for full speed operation. All of the above demand very high quality transmission lines from a signal integrity standpoint. The real world result is much shorter channel lengths and ever increasing PCB material costs. Utilization of internal to the server, high speed cabling is also on the rise.
That's right, and you know there are a lot of mechanical considerations that come along with this in design. So, you know, we're facing cooling challenges as you know we proliferate cables within the server, and as power requirements rise, and we're starting to see a need for more composable solutions, which also demand commonality based on open standards like I referenced before. So all these challenges and cost pressures are what are driving OEMs like HPE and Dell to look for new solutions.
Everyone listening, I know it's a lot of information to digest on one slide, so we'll continue to get more details as we proceed. Historically, modern server design has had several different eras. Wait for the next slide to come up. The era of single processors. shown in blue, was the time of an ever-increasing clock speed. CPU silicon was able to clock at ever-increasing speeds. It went from gigahertz to megahertz up to gigahertz. But at about 3 to 5 gigahertz, we've seen this era end. Next came the era of more cores. As we see on this graph on the right, on the left, excuse me, we see the socket performance is always increasing. During the same time period, the cost of transistors, our ability to pack even more and more stuff or transistors into a piece of silicon, the cost has come down per transistor. The graph on the right demonstrates this.
So, can you help me understand how these larger CPUs cause problems to the server design?
Sure, Rachel. I would say that our infrastructure is maxed out. If we go to the next slide, let me illustrate this with a graph. It shows the pressure the CPU, the server designers had over the last 7 to 8 years. As shown, the growth of core count within a socket has been growing exponentially. Currently, we're sitting 32 to 64 cores in our shipping products. But the processor companies and the processors themselves will have significantly more cores are expected to be on the market in the near future. There is no growth, there is no end to this growth in sight. Additionally, the number of memory channels and the PCIe lanes continue to grow as a result. And as I stated earlier, the current processors have over 4,000 pins per each device, and we believe that'll continue to grow. So let's score each of these areas as we go through. If we look at the cores per socket, obviously, as I stated earlier, that's increasing. The I/O bandwidth per core is decreasing. The memory capacity per core is increasing, i.e., every core wants more. The cache per core is fairly steady, but the resulting memory bandwidth per core is decreasing, and this is the significant problem. Memory bandwidth through IPC or interprocessor communication per core is decreasing. This is another significant problem, and the local memory latency is also increasing.
So, Greg, John, I hear you. It looks like infrastructure is totally maxed out. So, John, can you, do these trends have any impact on the mechanical form factor and system design?
Yeah, absolutely, Rachel. So, you know, as we attempt to feed memory to these growing core count that Greg referred to, we're adding additional channels of DDR, or we're trying to drive the DDR bus faster, or we're doing both. And so adding DDR channels significantly drives up CPU package pin count, which we mentioned before. And so this increases the physical size requirements for the processor. And then this all just consumes valuable real estate that we need to add extra connectors and memory modules as we add channels. And this increases cost, complexity, power consumption, et cetera. So all the additional challenges. And so also when we try to drive the DDR bus faster, you know, we have to accept additional overhead penalties on power, but also on sometimes error handling and on capacity to be able to deliver those higher speeds. So in this server image, this is a top-down view of a typical 2U server. On the right-hand side, you've got the storage bays. Right behind those, a bank of fans for cooling. And to the left-hand side, you've got your power supplies and PCIe adding cards. And so what's left there in the middle is the CPU memory complex. So in this server, you can see there's two of those large heat sinks. Underneath each is a processor. And then you can see either side of the processor is flanked by DDR memory modules. And so in this representation, you can see we're going wall to wall, the full width of a 19-inch rack. And so as you try to add additional modules and grow the CPU simultaneously, we start getting squeezed in that direction. And then at a certain point, you start to break and you can't pack it in any tighter. So that's where you can see we're running out of physical space.
John, isn't that problem even more acute in some dense server designs?
Yeah, certainly. So, there are a lot of, higher density server designs out there, typically in either HPC deployments or bladed servers. And so in those type of server designs, the processors are actually back-to-back. And so in these denser designs, you've got a thinner chassis, and just waiting for the slide to catch up here, but you can see in this image that with the processor memory complex being back-to-back, the memory modules are still pressed up to either side as we try to increase the density of these systems. And so this just adds to cooling, routing, and all those space limitations are magnified.
Wow, we got that image up now.
Go ahead, sorry.
No, I was just saying the image is up now. You can really see how dense it is.
Yeah, earlier you stated that the memory is changing. Greg, can you tell a little bit more about that, or talk a little bit more about that?
Yeah, we'll go to the next slide. The speed of memory is historically has a spectrum, and the speed historically we have storage silicon is approaching speeds that can be right now. We can start using them as load store memory in servers. The spectrum of memory technology is wide and has unique characteristics. The diagram that's shown here kind of represents this. On the far right, we have disk drives or even tape. Still exists. Flash memory is a newer entry into this type of memory, which over the years has been referred to as storage. And the main characteristic of storage is that it's persistent, i.e. the data survives power cycles. It's also usually organized in some kind of block structure, which through software is accessible. On the left-hand side, we have load store memories, which really do not require software to access. The memory is directly readable or writable by byte addressability. This includes processor registers, SRAM inside the processors, generally forming some kind of caching scheme, and of course DRAM in the form of external DIMMs we've already talked about. All these byte addressable load store memories are volatile and do not survive power outages. We have a new class of memory which we call storage class memory, which is a new entrant in the spectrum of memory. It is persistent, but it approaches the speeds of DRAM and is acceptable for the usage as a load store memory. The next slide. The rise of domain-specific devices challenges the way we've historically spend our transistors. This slide tries to illustrate the different ways we spend our transistors. Multiple vendors and multiple types of CPUs, x86s, power PCs, or the power architecture, ARM processors. We have new specific silicon for instructions being added into general purpose processors. We have storage class memory rather than just DRAM and SRAM. This memory is at speed, persistent, enterprise quality memories. We have smart NICs. These do tasks in the silicon to accomplish I/O relevant things like filtering, data reduction. We also spend our transistors on graphic processing units, or what we call GPUs. They've grown over their original usage as display rendering machines and now are key to many high-speed compute tasks. FPGAs, or field programmable gate arrays, have been around for many years. But now, because of their large size, integrated SoCs, and an easier way of methods of programming, these are being applied to specific workloads within the enterprise. Specialty processors, hard silicon designs that solve specific compute problems are being deployed.
So, given all the server design challenges and the emergence of all of these technologies, is there a solution to address this?
Well, I think there is.
Sorry, I was on mute. Yeah, so absolutely. Yeah, so several years ago, a group of companies got together and worked to develop a method of dealing with all of these issues. And so that ultimately they formed the Genz Consortium. So let's talk through that, some of the main tenets here. So Genz is a media and compute agnostic protocol. And so that means it allows for communication that abstracts above all the specific detail of a given media implementation. It's defined to be high bandwidth and low latency, and that's a kind of a fundamental premise that you need for any memory semantic interconnect. And Genz also embraces open innovation. So as we discussed as server architects, we see the need for open interconnects to avoid vendor lock-in. And so Genz is open-ended, and it's equipped to evolve with new technologies. So Genz also has high availability built in because it embraces the whole solution interconnect. And methods have been developed within the Genz protocol to ensure system uptime. And then finally, we developed it with security features, top of mind, built in from the beginning. So security, obviously, is a ever increasing feature we're looking for.
So, Greg, could you share some of the architecture attributes of Genz?
I sure can, Rachel. We'll wait till the slide comes up. I hear we're having a little bit of lag, but Genz uses a packet protocol to communicate between components. Components are either requesters or responders. This enables the protocol to scale from co-packaged to embedded to a single enclosure to a rack enclosure. Links can be composed of any number or mix of transmit and receive lines. We use two different types of physical layers for signaling. We use a PCIe-based SerDes or an 802.3 SerDes. They are optimized either for inside-the-box communication or outside-the-box communication. We've demonstrated speeds to 112 gigatransfers per second. The architecture supports a split memory controller, media controller functional paradigm. This memory controller takes care of all the high-level memory operations, and the media controller takes care of the media-specific logic. The two communicate using Genz protocol. It breaks what we call the processor memory deadlock that John talked about earlier, where we can start releasing new processor or new memory technology independent of one another, so they're not gated on one another. The Genz technology supports today's processor-centric architecture, i.e., where most communication passes through an application processor. This enables existing solutions to transition to Genz while minimum disruption to the overall ecosystem. The architecture also supports memory-centric architectures. In memory-centric architectures, the component can directly talk to memory or each other without going through an application processor. A memory-centric architecture reduces the amount of data movement, power consumption, latency, and other items.
So you guys have done a really great job describing how Genz technology could address some of the problems that customers are experiencing. But John, as co-chair of the Mechanical Working Group, can you describe the efforts being made to enable and build out the vision?
Certainly, yeah. So the working group set out to enable existing legacy form factors such as U.2, U.3 drives, PCIe, chem cards, OCP form factors, so that Genz could out the gate be used across the broadest set of use cases. But beyond that, we saw the need for new connector solutions and some new form factor solutions as well. So we developed a new scalable connector within the work group, and that was transferred to the SFF industry body within SNIA, and that was done to maximize industry adoption of that connector. And we also created a new modular mechanical form factor that's intended to reduce mechanical fragmentation and maximize chassis reuse within a set of systems. So these are two of the most foundational components in server design, connectors and form factors. And we really designed them to address the limitations of legacy designs that we've already discussed. So it's also important to note that all of the form factors and connectors that we're going to discuss here are protocol agnostic. So that means they can be used for any device across the industry, and the consortium actively encourages that. So here you see, because Genz enables any media to be connected within the same ecosystem, we identified a need for a methodology that allows a chassis to accommodate this wide range of devices with their wide range and variety of power, size, and connectivity requirements. And so what you're seeing here are just some examples of how a system could be built in a modular fashion in which each compute element is based on a common building block defined within a framework. So this allows chassis designers to implement scalable systems that are space planned to accommodate any resources that may be attached to Genz. And so to go into a little more detail on that, so the working group, we defined a methodology to enable a scalable form factor, and we built it on the existing fundamental building blocks that we have in the industry that kind of govern us all. So specifically, that would be like a 1U volumetric, or the thinnest pitch possible of PCB assemblies with common manufacturing practices. And then in addition to that, we defined tolerances based on those common manufacturing processes that are used across the industry, and we scale them along with the nominal dimensions so that we can build out the table of dimensions you see here. So the details of this, they're documented in the Genz ZSFF specification. And so if you would like to learn more about the nuts and bolts, and I encourage you to go look at that. But for our purposes here, I'll focus on how this scaling framework can be and has been implemented. And so what you see in the bottom left-hand corner there are examples of media modules designed for high-power DRAM or storage-class memory devices, or for lower-power NAND-based devices. And then on the right-hand side, you can see form factors that were designed for larger SoC, GPU, accelerator modules. And so the media devices on the left were actually derived from the framework and standardized also within SFF under SNIA as SFF TA1008, which is probably more commonly known as EDSFF 3-inch or E3 modules. And so I encourage folks to go take a look at those as well. So then, as I mentioned before, another primary focus of the work group was a high performance and scalable connector that could accommodate the variety of requirements that these devices would have. So the Genz connector we developed at a high level, it's a card edge, high density, discrete pin connector, supports vertical, right angle, even their straddle mounts, cabled installations, etc. And again, this is all documented in SNIA, in the SFF working group as TA1002. And so this connector provides high performance signal integrity, which is very important. So that's capable of supporting line rates up to 112 gigatransfer per second PAM4. And this also enables a FEC-free or low FEC, low latency ecosystem for Gen Z, which, as I mentioned before, was one of our key design metrics. And so we'll discuss the benefits of superior connector signal integrity in a few more minutes. But first, I wanted to jump into another form factor that was developed. And so what we're showing here is a form factor that both Dell and HPE see immediate value in. And so we call this the PCIe Enclosure compatible form factor. It rolls right off the tongue, PECFF for short. And it's essentially a standard PCIe chem form factor with all the same scalability that currently exists in that form factor, half length, double high, full high, etc. But on this, we replaced the chem connector with the Gen Z connector, or the TA1002 connector. And so by doing this, we maintain chassis compatibility. So we have all the same mechanical interfaces that you have in existing PCIe cards, but we made some tweaks along the way to enable a couple of benefits. So one is better stacking in a one-use system. And so for those who are intimately familiar with designing systems for PCIe cards, we made a few tweaks there to make it easier to stack in a 1U. And we also looked at, there's an emergence of card-to-card cabling that's coming out in the industry. And so we wanted to provide some enablement around that to make sure that card-to-card cabling can be achieved and there's enough connectivity there, but also so that it stays within the form factor to enable broader adoption. And another thing we did on the connector side is we enabled inline power delivery. So chem cards today use secondary or tertiary cables to cable up extra power from a host into an add-in card. And so this form factor defined a high power inline card edge to do that power delivery without the need for cables, which is a big win from the system side. And then of course on the connector we get the superior connector SI, but beyond that we reduced the overall trace length requirements by about 60 millimeters. And so what that does is it allows for more channel budget to be used elsewhere in the system and or enables a power reduction in either the host or add-in card ASICs because they don't have to drive as far. And so we also, on top of that, wanted to establish support for a 48-volt ecosystem. This is something we're starting to see coming out in the market more, is 48 volt for very high power solutions. And so this is, in addition to, we added up to a by 32 interface. And so all of those features are kind of coming together, are why we see immediate value here for this form factor.
So earlier you'd mentioned that signal integrity is a concern for server architects when considering the higher communication speeds. Greg, would you mind expanding on that just a bit with this slide?
Yeah, the ZSFF TA1002, the connector John was just talking about, has very good performance at Gen Z frequencies. This slide actually captures some of the test results that we've seen on the connector. As noted, we're using a PNA analyzer, and it has capabilities up to 50 gigahertz. The lower left shows the insertion loss versus frequency, which is far less than the limit line. The middle graph shows return loss, and the two graphs on the right show the performance of far and near-end crosstalk, all under the limit lines. So we're very happy with these performances.
Yeah, so to expand on the importance of SI performance even further, and how that directly impacts system designs. I'd like to talk about some channel simulations. So that's going to come up here on the slide in a second. And so basically what you're going to see is 3 channel simulations that are all identical, all except for the connector. So in one channel, we use a PCIe connector, while in the other, we use the TA1002 connector. So in the lower left-hand corner there, you can see simulation 1. It's an optimized channel, optimized features, impedance, etc. And you can see there's a clear benefit to using the TA1002 connector. It's on the order of about 10%. However, in simulations 2 and 3 that you see on the right-hand side, what we've done is introduced manufacturing variations on the order of plus or minus 10%. And what we're illustrating here is that the channel, as you can see with the PCIe connector, starts having the I width collapsing, actually in collapsing below the error threshold when you introduce these variations, because in real world manufacturing there are variations. Whereas the channel with the Genz connector, the TA1002 connector, it's actually more resilient and stays above that error threshold. And so this is the kind of resiliency and flexibility that you need in the real world, and it's the primary driver behind the consortium developing both the PECFF standard and the connector standard. And it's behind why OEMs like HPE and Dell are wanting to adopt it, to take advantage of these benefits in real-world systems.
So with all the background information that you've both provided, Greg, could you describe what a memory-centric server architecture might look like?
Sure, Rachel. A memory-centric architecture would have a pool of shareable storage class memory devices, shareable server resources, shareable accelerators, which I call domain-specific processors. They would be interconnected through some assignable memory fabric. The system would would understand native load store instructions and communicate them end-to-end as efficiently as possible. This would be required for full disaggregation. Clearly, the Genz protocol, along with all the switching fabric, accomplishes this, and providing low latency, high bandwidth communication with load store. Inside the chassis, Genz could support a large quantity of local SCM. Additionally, if the chassis was larger and could accommodate a large number of domain-specific processors, specifically GPUs or FPGA accelerators, Genz can be directly utilized inside the chassis. Bridging may be required from one technology to another, coming out of processors. Going to the next slide. Our real goal in system resource utilization, I want to illustrate how disaggregation can help. Servers are composed of a set of resources. This diagram shows processors, memories, GPUs, storage, communication. An application or workload is applied to this system, and because there was no right sizing of the number of resources, the server had to be designed to accommodate the largest usage possible. So utilization resource of those resources is low, probably less than 20% on average. With the introduction in the middle of virtualization software, VMware, Xen, there's many others, multiple applications could take advantage of being loaded simultaneously on the same set of hardwares, applied to the same set of resources by using these methods. Utilization was increased, but all the resources were not fully utilized because of system structural issues. The hardware was not totally disaggregated. The memory behind the CPU was not totally accessible. So Genz enables a total disaggregation where all components have equal footing and are interconnected by a scalable fabric. So now applications can be loaded and resources can be assigned in a very strategic for optimal utilization.
So John, do you want to tell us about the benefits of disaggregation for system designers?
Yeah, sure. So, you know, what full disaggregation really brings us is the ability to compose servers with the resources that an application requires. You can unlock trapped resources that otherwise would be behind or tied to a CPU. In the case of memory, you can unlock those, bring them out in a disaggregated system and assign them dynamically. And then you can also avoid over provisioning. You know, it refers back to that underutilization problem. And then, of course, you can purchase these resources independently. So you have a much more effective cost operational model. And all at the same time, you can increase your RAS features, and you can repurpose any retired resources. And, you know, like we mentioned before, that you can evolve technologies independently and deploy them independently, as opposed to waiting for some big bang release and tearing everything up and starting over.
So with everything going on, I know you guys are going to be at Supercompute next week in Denver. Greg, could you tell us a little bit about what Genz is going to be showcasing there?
Sure. Why don't we pop up the next slide? There it is. At Supercompute, Genz is demonstrating our next step of our goal of total disaggregation of the server environment. We have a rack with multiple vendors. We have HP, Dell, IBM, Samsung, SK Hynix, which have both servers and appliances, both in and outside this rack environment. We talked earlier about ZMM, Genz Media Modules. Smart Modular has several versions of that there. Additionally, FPGA and firmware and software being demonstrated by multiple vendors, including IntelliProp. The diagram shows that interconnect.
Yeah, and we'll also have a full array of the mechanical form factors, connectors that we talked about on display. So, you know, we encourage everybody to come by and check it out.
Thank you so much, Greg and John, for all of the information that you've shared in this presentation. I know we do have some questions from the audience. We were saving those for the end, and love to have you guys answer those. If you're ready, I can start posing those for you. You ready?
Sure, absolutely.
Sure thing.
Okay, so the first question that I have is, how does Genz reduce pin count and increase bandwidth into a processor's socket?
Well, I will take first stab at that, and John can follow up. First thing is the typical interface for Genz is somewhere in the neighborhood of 140 some odd pins, I believe, and I think a standard DIMM is in excess of 300 pins in round figures. And the bandwidth is significantly higher on a Genz interface, and so that would be one of the motivations for moving over to a Genz interface, because you get more bandwidth per pin. And if people remember from DDR still a single-ended interface as opposed to differential, which gives us better signal integrity and all the things we've been talking about. John, do you have any other input on that?
Yeah, you know, I guess the even more technical answer to that would be that Genz is a differential signaling when you compare it to DDR, which is single-ended, and so you just by its nature you gain a very, very good pin count advantage.
Yep. I hope that answers the question.
Great. Yeah,
Yep.
If there are any follow-up questions, we can certainly answer those offline afterwards. And then also, if anyone does have any questions, please do continue to submit those through the questions option on your BrightTalk slide. So next question, we've had a couple of folks actually asking about this in various and sundry ways, so I'm going to summarize it. And basically the question involves Genz and CXL, you know, Genz given the announcement and formation of the CXL consortium. So can you two talk a little bit about how CXL and Genz intersect with one another, how they're going to work together if they are, how Genz is going to evolve, et cetera?
Sure, I'll take that. Genz is a complete and robust fabric that is used on various configurations and was architected and designed to be an interconnect to run peripherals located centimeters apart or meters apart. It allows for all these CPUs we talked about and GPUs, avoid time and power consuming required in the current architectures that are required to move this data. CXL and Genz are common and have common members and are seen by the industry as highly complementary interfaces. In fact, I'll even go down this path. Genz provided a quote on the launch of CXL, welcoming them to the industry. As a matter of fact, the person that gave the quote was the president of Genz and has maintained a great relationship between the two consortiums ever since. So we do see, and I did allude to bridging. CXL is an excellent product of coming directly out of the processors. John, do you have anything to add in this area?
No, I think you covered it.
Okay,
yeah,
very good.
Very complimentary. Yeah.
Great. So we're getting a couple of questions about sharing the slides. We will have the slides, and the full webinar will be available for on-demand viewing following the webinar. So folks that are interested in that, you can come back, review the webinar, as well as download the slides.
Rachel,
the next question, yes.
If they happen to be in Denver, we'd sure like to talk to them straight away.
Oh, absolutely. Yeah, if you're going to be in Denver next week for Supercompute, we would love for folks to stop by our booth. It's booth number 789. And you're welcome to stop by, check out what we're going to be showcasing, and ask any questions you might have in real time. Great. So a couple of other questions we do have. Do you expect Genz to eventually utilize onboard optics in place of the traditional QSFP media?
Yeah, I can take that one, Rachel. So, you know, Genz as a consortium within the mechanical working group, we looked at areas that we felt were needed to be worked on, like connectors and form factors, to really enable the vision that we've been looking at. Now, Genz as a protocol can be carried across any interface. It can be carried across passive copper, active copper, optical, etc. And so the consortium has, in the Genz connector spec, when it was first published, mentioned working on external connectors, but at the moment I don't think we have external facing connector development plans, simply because when we look at the variety of solutions that are out there, you mentioned QSFP, QSFP-DD, CXP, SFP, etc. There's a lot of things, there are a lot of options out there already that people are executing on. And so Genz can be carried on onboard optics. It can be carried through QSFP devices. As a protocol, it's agnostic of those.
And that will be demonstrated. The agnostic nature, our rack communication at Supercompute is through QSFP cables.
Yeah, that's correct.
So here's a question we've gotten a lot actually in the past, and then again just now in this webinar. It's a question around product offerings from vendors that are using Genz. It's around time frame and that type of thing, but I think you guys might have an answer for that. Can you tell us when or if products are going to be developed that are using Genz technology?
Sure, we can venture down this path. Obviously, to be cost effective for large providers of server technology, FPGAs are very good for doing initial concept development. We're doing limited production, but to be in a high volume, we really have to have hard silicon, and we have several members of our membership that are actively going down and looking at the opportunities for developing hard silicon, for switching aspects, for bridging aspects, for responders, requesters. Silicon development does, as everyone knows, take a little time, so I cannot speak for them, but one could anticipate inside somewhere around a typical silicon design time, is as close as I could come.
Yeah, and I'll just add to that beyond the silicon and protocol itself, we've already had fairly successful adoption of the form factors, especially the connector. And so the TA1002 connector is seeing fairly broad industry adoption on a wide variety of devices that are outside of the purview of Genz completely. I mentioned ZSFF. There's DDIM from JEDEC that was recently published. OCP NIC 3.0. Yep. Mm-hmm. So yeah, you can. Those are all out there. You can and getting adopted, and so there's systems in flight to pick those up.
And my understanding too is that we'll actually have some working items within the booth at Supercompute. Is that correct? I believe so.
Yes.
There'll be a number of things.
Go ahead.
Great.
I was just going to say there's a whole host of demonstrations we're going to have in the booth. Greg mentioned going over optical cables, showing Genz over a fabric. We have a rack that we've shown in the past, and we've updated and have additional content to show. So, yeah, there'll be a lot to see.
Great. So I have one more question that has come up. The question is there a sort of operating system for the presented hardware?
Greg, that's probably a better question for you. I'm the mechanical guy.
Yeah. And I'm the electrical guy. This is a software question. I would encourage some people to get involved and ask the questions directly to our software teams. But in general, once we've established a load store system, then the operating system can take advantage of these memory resources just as it would any other memory resource. In the interim, we have methods where we can declare logical PCIe devices, and we can communicate across that, but that's probably not the end case where we want to be. Where we want to be is where we're load store, and so it presents itself into the operating system just as regular memory, and would be the operating system would be unaware that it's talking to Genz memory as opposed to DIM memory or any other kind of memory.
Yeah, and I'll just add to that. I think there's been some tutorials posted to the Genz site that refer to what can be accomplished with an unmodified OS. But there's also a kind of development environment for software that has been published to, I think it's on GitHub. And
yes.
We've demonstrated that at SC18 last year. It's an emulator, that's the word I'm looking for this environment to allow development to work. And that's totally open. People can go pick that up and play with it. And if you're interested and you're in Denver, come on by and you can probably have a look.
Another area that we're demonstrating at Supercompute is the concept of in-memory compute appliances, and SK Hynix and Samsung both have demonstrations of where the protocol is responding to stimulus for some kind of in-memory compute. So I don't have the full details, but I'm excited to get educated on that myself when I get there.
Thanks so much, guys.
Yes.
This is really great discussion, and we appreciate so much you sharing all of the information that you shared with us today. I know that folks are going to want to learn more about Genz. So I want to make sure that we share some information with you that you can use to gather more details about Genz. So if you want to learn more about Genz and its industry support, you can definitely visit our website at genzconsortium.org. And again, we've just done this webinar today. We do have a couple of previous webinars that we conducted. Those, as I mentioned, are available for on-demand viewing on the Bright Talk channel. So please do make sure you download those. Very interesting topics, providing a general overview of Genz as well as discussion from Mike Krause about the built-in security systems within Gen Z technology. So really, really great information there. You can also follow us on Twitter at Gen Z Consortium and on LinkedIn for real-time updates, where we are, what events we're attending, what's happening, what we're presenting. So make sure that you are following us on those social media channels, and make sure you look for the latest videos from Gen Z on our YouTube channel, which we are constantly adding new items to, and I'm certain we will have more after this upcoming event next week in Denver. So again, we want to thank John and Greg for presenting today, for sharing the information that you did share, and also remind everyone, I think we mentioned it once or twice, but I'm happy to mention it again. We will be at Supercompute next week, and Gen Z will be located in booth number 789. We hope if you are going to be there that you can stop by and visit. And John, Greg, I believe both of you will be there and ready to answer any questions that folks come at you with. Is that correct?
Yes, it is, and thank you everyone for attending.
That is correct. Yeah, thank you very much for everyone attending. Appreciate it.
Great. Thanks, everyone, and take care.